Download this code from codegive.com, link in the description below. OK, let's dive into heap sort, covering both recursive and non-recursive, iterative, approaches, along with a detailed explanation and code examples in Python. We'll also touch upon the heapify operation and discuss copying. Understanding heap sort. Heap sort is a comparison-based sorting algorithm that leverages the properties of a binary heap data structure. Here's a breakdown of the key ideas. 1. Heap data structure. A heap is a specialized tree-based data structure that satisfies the heap property. In a max heap, for any given node I, the value of node I is greater than or equal to the values of its children. A min-heap has the opposite property. The value of a node is less than or equal to its children. 2. Building a heap. Heap sort starts by building a max heap from the input array. This involves arranging the elements in the array to satisfy the heap property. 3. Sorting. Once the max heap is constructed, the algorithm repeatedly extracts the largest element, the root of the heap, places it at the end of the sorted portion of the array, and then heapifies the remaining elements to maintain the heap property. This process continues until all elements are sorted. Steps of heap sort. 1. Build max heap. Convert the given array into a max heap. 2. Repeatedly extract max and heapify *. Swap the root element, maximum element, with the last element in the heap. Reduce the heap size by 1. Heapify the root of the heap to maintain the max heap property. Code example, Python, both recursive and iterative heapify. Explanation *. Heapify _ recursive, arr, n, I, *. Takes the array arr, its size n, and the index I of the root of the subtree to heapify. It finds the largest element among the root arri and its left and right children. If the largest element is not the root, it swaps the root with the largest element and recursively calls heapify on the affected subtree to ensure the heap property is maintained. This recursion continues until the heap property is satisfied at that node and its descendants. Heapify _ iterative, arr, n, I, *. Does the same job as heapify _ recursive, but uses a while loop instead of recursion. Inside the loop, it checks for violations of the heap property and swaps elements until the subtree rooted at I is a valid max heap. The key is to update I to be the index of the child that was swapped, so that heapifying continues down the tree from that child's position. Build _ max _ heap, arr, *. Takes the array and converts it into a max heap. It iterates from the last non-leaf node, index n/2, 1, up to the root, index 0. For each node, it calls heapify to ensure that the subtree rooted at that node satisfies the max heap property. Iterating in this order ensures that all subtrees are heapified before their parents, which is crucial for correctness. Heap _ sort, arr, *. The main heap sort function. It first calls build _ max _ heap to create a max heap from the input array. Then, it iterates from the last element, index n, 1, down to the second element, index 1. In each iteration, it swaps the root, maximum element, with the element at the current index I. This places the largest element at its correct sorted position at the end of the array. It reduces the heap size effectively by decrementing I. It calls heapify on the reduced heap, root index 0, to maintain the max heap property for the remaining unsorted elements. Heap _ sort _ copy, arr, *. This function creates a copy of the input array using arr. It then calls the standard heap _ sort function on this copied array. Finally, it returns the sorted copy, leaving the original array unchanged. Recursive versus iterative heapify asterisk. Asterisk recursive heapify asterisk more concise and easier to read for some. However, deep recursion can lead to stack overflow errors for very large arrays, although this is less of a concern in Python than in languages like C/C++ due to Python's handling of recursion. Asterisk iterative heapify asterisk avoids the risk of stack overflow. It might be slightly more complex to read initially, but it is generally considered more robust for large inputs. Why build the heap from the last non-leaf node upwards? This is crucial for correctness. Consider building the heap from the root down. If you heapify the root first, you might swap it with one of its children, creating a violation of the heap property deeper in the tree. You then need to fix those violations, potentially requiring multiple passes. By starting from the last non-leaf node and moving upwards, you ensure that all subtrees are already valid heaps before you heapify their parent. This guarantees that each call to heapify correctly places the current node in its proper position within the heap, leading to a valid max heap in a single pass. In-place sorting. Heap sort is an in-place sorting algorithm, excluding the heap_sort_copy function, which intentionally creates a copy. This means it sorts the array directly within the original memory space, without requiring significant extra memory allocation. It uses O(1) extra space. The copying example needs O(n) extra space. Time complexity. Asterisk building the heap asterisk O(n). Asterisk heap sorting asterisk O(n) log n, because each extraction and heapify operation takes log n time, and you do it n times. Therefore, the overall time complexity of heap sort is n log n, in the best, average, and worst cases. Space complexity. Asterisk heap sort, in place O(1), constant extra space. Asterisk heap sort with copy asterisk O(n), linear extra space for the copy. When to use heap sort. Asterisk guaranteed O(n) log n, performance asterisk heap sort provides consistent performance, making it suitable when you need a reliable upper bound on the sorting time. Asterisk in-place sorting asterisk if memory usage is a major concern, heap sort's in-place nature is an advantage. Asterisk priority queues asterisk the underlying heap data structure is heavily used in implementing priority queues. If you need a sorted structure that allows for efficient insertion and retrieval of the highest, or lowest, priority element, a heap-based priority queue is a good choice. Limitations. Asterisk not stable asterisk heap sort is generally not a stable sorting algorithm, meaning that elements with equal values might not maintain their original order after sorting. Stability is important in some applications where the original order of equal elements matters. Asterisk less cache-friendly asterisk the memory access patterns of heap sort can be less cache-friendly compared to algorithms like merge sort or quick sort, potentially impacting performance in practice, especially on very large data sets. Cache friendliness refers to how well an algorithm utilizes the CPU cache, which can significantly affect performance. Copying the array, important for preservation. In many situations, you'll want to sort an array without modifying the original array. That's why the heap_sort_copy function is important. The ARR syntax creates a shallow copy of the array. This means a new array object is created, but the elements inside the new array still point to the same objects as the original array. For basic data types, numbers, strings, this is effectively a deep copy. However, if your array contains mutable objects, lists, dictionaries, changes to those mutable objects within the copied array will affect the original array. If you need a fully independent copy, a deep copy, you can use the copy.deepCopy, Function from the copy module. Using copy.deepCopy ensures that all nested objects are also copied, providing complete isolation between the original and the copied arrays. However, deep copying is more computationally expensive than shallow copying. I hope this comprehensive explanation clarifies heap sort. Let me know if you have any further questions.